They sour. They react with active metals to produce hydrogen gas, and they react with carbonates to produce carbon dioxide. When you mix them with bases, they tend to neutralize bases. A lot of household products, such as citrus fruit, are examples of acids. Bases, on the other hand, taste bitter. They are slimy to the touch, and they neutralize acids when they are mixed. Common household products that are bases are generally cleaning supplies or soaps and detergents and things of that nature. Definition of an acid or base, well, the definition that we've been discussing so far is an acid is a substance that produces hydrogen ions in solution. Here's an example. As you can see here, HCl, when it ionizes, it becomes H plus ions and Cl minus ions. When it ionizes as an H plus, that is an indicator of an acid. A base produces hydroxide ions in solution. So, when a base comes in contact with water, or when it's by itself and deionizes, it ionizes into hydroxide ions, as you can see in the bottom two examples. However, we need to identify acids and bases if we don't have hydroxide ions or we don't have H plus ions. So Bronsted-Lowry came up with another definition. An acid is a proton donor, and bases are proton acceptors. An acid-base reaction is basically the transfer of a proton from an acid to a base. As you can see here, this hydrochloric acid mixed with water is an example of an acid-base reaction. Okay? But in this case, base is not an OH. It's actually the water, because the water is accepting the proton from the hydrochloric acid. As you can see on the other side, the Cl minus is without the hydrogen, and the H3O plus is water with one more proton. Again, HCl is the acid, which donates the proton, and in this example, water is the base, which accepts the proton. Let's take a look at another example. We have NH3 plus H2O makes NH4 plus OH minus. Well, in this case, as you can see, water loses the proton, so therefore water is the base, and NH3 gains a proton, so therefore it is the base. Okay, NH3 is the base, H2O is the acid. There's different types of acids. There's monoprotic acids, an acid that can furnish only one proton, a diprotic acid which can furnish two protons, and a triprotic acid which can furnish three protons. The acid strength depends on how easily this acid will give up the proton and become completely ionized. Strong acids completely ionize, and examples include hydrochloric acid, nitric acid, and sulfuric acid, increasing in strength. Sulfuric acid is the strongest acid. Weak acids do not completely ionize, and they include acetic acid. Conjugate acid-base pairs. Conjugate acid-base pairs are a reactant and a product that differ by only one proton, an H+. Here's a generic equation. HA is the acid, B- is the base, and it goes to HB, which is the conjugate base, and A-, which is the conjugate, HB is the conjugate acid, and A- is the conjugate base. So as you can see here, this is a conjugate acid-base pair, and here is another conjugate acid-base pair. Take a look at this example. We have HF plus H2O, make H3O plus F minus. As you can see here, these two, HF and F minus, are a conjugate acid-base pair, and H2O and H3O plus are a conjugate acid-base pair. This, for general purposes, NO is called a hydronium ion. So, taking a look here, let's do some examples here. HCl plus H2O make H3O plus Cl minus. As you can see here, this is an acid and its conjugate base. And this right here is a base. Oops, this is a base. H2O is a base, and with the H3O plus, that's the conjugate acid. Key point. Every acid has a conjugate base formed by the removal of a proton from an acid, and every base has a conjugate acid formed by the addition of a proton to the base. Conjugate acid and base have strengths, just like acids and bases have strengths. The more readily a substance gives up a proton, the less readily its conjugate base accepts a proton. And the more readily a base accepts a proton, the less readily its conjugate acid gives up a proton. Key point, the stronger the acid, the weaker its conjugate base. The weaker an acid, the stronger its conjugate base. As you can see by this table here, these are acids and bases by strength. Acid strength goes up, base strength goes down. The acid on the other column would be its conjugate base, and as you can see there, it has a weak base. On the other side, you have a weak acid, NH4+, but its conjugate base is really strong. Buffers use weak acids and their strong conjugate bases. So the only example I want you to understand or know of a buffer is acetic acid, which is CH3COOH. It's just written a different way. And sodium acetate. Sodium is therefore removed because the acetate is the only part that really is the conjugate base in this case. CH3COO minus. So what are buffers used for? They're used to keep the pH from increasing or decreasing too dramatically. How does it do it? Well, the acid neutralizes the OH in solution, and the conjugate base neutralizes the H plus in solution. Water is not a buffer, however. Water is called amphoteric. Amphoteric means that it can act as either an acid or base. An example of this is NH3 plus H2O makes NH4 plus OH minus. As you can see in this example, the water is the acid. In this example, HF plus H2O makes H3O plus F minus. And in this case, you can see water is acting as a base.